Another question for the equilibrium playlist. So this one covers features of a dynamic equilibrium, a KP calculation, and Le Chatelier's principle. As always, the link to the questions in the description of the video if you wanted to try it first. Okay, so make a start. So other features of a dynamic equilibrium, you could say the rate of the forward reaction equals the rate of the reverse reaction. Or you could say the concentration of all the species in the reaction remain constant or don't change. Moving on to part B in the calculation, so I've put together an ICE table, so initial change equilibrium. So these are the moles we're told at the start. Obviously there's no NO2 to start with. We're told that 75% of the NO has been converted to NO2, so that means 75% of this has reacted, which means it's going to drop by 1.2 moles, so at equilibrium we're left with 0.4. The mole ratio means that only 0.6 moles of O2 is going to react, so that means there's 0.9 moles left, and the mole ratio also tells us that 1.2 moles of NO2 will form, because that's a 1-to-1 ratio. So now we'll work out the total moles at equilibrium, which comes out at 2.5 moles, so the mole fractions now is going to be the moles at equilibrium divided by the total moles. So there they are there, and now we need to multiply each mole fraction by the total pressure to get the partial pressure. So there's the partial pressures there. So all we need to do now is construct the Kp expression and put these partial pressures in, which gives a Kp value to three significant figures of 20.7. And finally, the last part of the question where we've got to look at the effect of these changes on Kp, the equilibrium amount of NO2 and the initial rate. So we'll take temperature increase first. So we're looking at the sign for delta H. So the forward reaction's exothermic. So if you increase the temperature, it's going to favour the endothermic reaction, which is the reverse reaction. So Kp is going to get smaller because the partial pressures of these are going to increase and that's going to decrease. So because it's gone backwards, the equilibrium amount of NO2 is also going to get smaller. The initial rate is going to be greater because obviously higher temperature, more kinetic energy for the particles. Moving on to the pressure increase, so Kp is only affected by temperature, so it's going to stay the same. Increase in pressure favours the side with the fewest moles, so this is going to move forwards, which means the NO2 amount is going to be greater. And an increase in pressure leads to a higher rate of reaction, so the initial rate is going to be greater. And finally, the addition of a catalyst. Well, we've already said temperature is the only thing that changes Kp, so it's going to stay the same. The equilibrium amount of NO2 will be the same because catalysts don't affect the position of the equilibrium. Addition of a catalyst will increase the rate of the reaction, so the initial rate will be greater.